Picture this: far beyond our Milky Way, in the darkest corners of space, there are objects so bright they defy everything we know about physics. These aren't stars. They're not even supermassive black holes. They're ultraluminous X-ray sources, cosmic monsters beaming out energy at levels that shouldn't exist. Some shine millions of times brighter than our entire sun, yet they're smaller than a city. How is that possible? What could possibly power something so unimaginably intense? For decades, these mysterious objects have baffled scientists. They break the rules, challenge our theories, and force us to rethink the limits of the universe. Some might be black holes feeding at impossible rates. Others could be neutron stars with magnetic fields so strong they warp reality itself. And then there's the wildest possibility: something entirely new, a type of cosmic engine we've never seen before. Stick around, because today we're diving deep into the enigma of ultraluminous X-ray sources. By the end of this video, you'll understand why these celestial powerhouses are rewriting the textbooks, and what their secrets could reveal about the most extreme physics in the cosmos. This isn't just science, this is the edge of human knowledge, and you're about to step right up to it. Now, let's get to the heart of the matter. What exactly are these cosmic powerhouses? Ultraluminous X-ray sources, or ULXs for short, are some of the most extreme objects in the universe. Imagine a single object no bigger than a city, blasting out X-rays with the energy of millions of suns. That's what we're dealing with here. These aren't your average black holes or neutron stars. There's something far more intense, pushing the boundaries of what we thought was possible. Scientists first stumbled upon ULXs in the late 20th century, using early X-ray telescopes. At first, they assumed these bright spots were supermassive black holes at the centers of distant galaxies. But there was a problem. These objects weren't where they were supposed to be. Instead of sitting in galactic cores, they were scattered throughout star-forming regions, often far from the center. That's when researchers realized they'd found something entirely new. What makes ULXs truly stand out is their sheer brightness. Even the most powerful stellar mass black holes, which can devour entire stars, have a theoretical limit to how much energy they can emit, a rule called the Eddington limit. But ULXs blow right past that limit, shining hundreds or even thousands of times brighter than they should. That's like finding a flashlight outshining a stadium full of spotlights. It shouldn't happen, yet here they are, defying the rules and forcing us to rethink how matter behaves under the most extreme conditions. So why does this matter? Because ULXs aren't just cosmic oddities, they're windows into physics we can't recreate on Earth. Whether they're black holes feeding at impossible rates, neutron stars with unimaginable magnetic fields, or something we haven't even dreamed up yet, studying them could unlock secrets about gravity, matter, and energy at their most extreme. And that's just the beginning. Now, here's where things get really puzzling. If ULXs are breaking all the rules, how exactly are they pulling it off? The answer isn't simple. And that's what makes this one of the biggest mysteries in modern astrophysics. Take a stellar mass black hole, for example. Even as it devours gas from a nearby star, there's a cap on how bright it can get, the Eddington limit. This is the point where the radiation pressure from all that energy actually pushes material away, like a cosmic tug of war. But ULXs don't just nudge past this limit, they smash through it, shining hundreds of times brighter than they should. So what's going on? One leading idea is that these objects might be feeding at insane rates, gorging on material so fast that the usual rules don't apply. Picture a whirlpool sucking down water faster than it can spill out that Super-Eddington accretion. In this scenario, the infalling matter creates such a thick, chaotic environment that radiation struggles to escape, effectively trapping energy and letting the object shine far beyond its expected limit. But there's another twist. Some ULXs might not actually be as bright as they appear. Instead, their light could be focused into narrow beams, like a cosmic lighthouse pointing straight at us. If that's the case, we're seeing an illusion, a trick of perspective that makes them seem brighter than they truly are. This beaming effect could explain why some ULXs appear to defy physics without actually breaking the rules. Then there's the neutron star possibility. A handful of ULXs have been caught pulsing like cosmic heartbeats, which means they're likely neutron stars with insane magnetic fields. These magnetic monsters could channel energy into focused jets or distort the surrounding space so much that they temporarily cheat the Eddington limit. It's like squeezing a fire hose to make the spray more intense, except here, the hose is made of space-time itself. The debate is far from settled. Some scientists argue for intermediate mass black holes, others for exotic physics we haven't even discovered yet. What's clear is that ULXs are forcing us to rewrite the textbooks, one mind-bending discovery at a time, and that's what makes them so thrilling. They're not just bright. They're beacons lighting the way to a deeper understanding of the universe's most extreme environments. Now, let's put ULXs side by side with the black holes we know best, stellar mass and supermassive ones, to see just how bizarre these cosmic overachievers really are. Picture a typical stellar mass black hole, the kind formed when a massive star collapses. It's no slouch. It can devour gas from a companion star and shine fiercely in X-rays. But even at its hungriest, it hits a wall, the Eddington limit. That's the point where radiation from its meal pushes back so hard that it stops more material from falling in, like a furnace so hot it blows its own fuel away. These black holes play by the rules, staying within their expected brightness range. Then there are supermassive black holes, the giants lurking in galactic centers. They're millions to billions of times heavier than the Sun, and their gravity is so strong they can swallow entire stars. Yet even they respect the Eddington limit, just on a grander scale. Their brightness scales with their size, so while they're staggeringly luminous, they're not breaking any fundamental laws. Now enter ULXs. These cosmic rebels don't just ignore the Eddington limit, they laugh in its face. Some shine hundreds or even thousands of times brighter than a stellar mass black hole ever should. If they were ordinary black holes of similar size, their radiation should have blown away their food supply long ago. But ULXs keep burning brighter, as if they've found a loophole in the universe's rulebook. So what's the difference? One clue lies in how they feed. Ordinary black holes consume matter at a steady, predictable rate, like a campfire burning logs. ULXs, though, might be gorging themselves in frenzied feasts, pulling in materials so fast that the radiation can't escape to push back. It's like trying to shout over a hurricane. Your voice just gets drowned out. Another twist, ULXs might not be playing fair with geometry. If their X-rays are beamed in narrow jets pointed right at us, we're seeing a spotlight effect, not true cosmic defiance. It's the difference between staring into a flashlight and seeing its glow from the side. But here's the kicker. Even if some ULXs are stellar mass black holes with tricky lighting, others, like the pulsing ones, are neutron stars, which shouldn't be this bright at all. That means no single explanation fits all ULXs, and that's what makes them so fascinating. They're not just brighter versions of ordinary black holes. They're a whole new class of cosmic puzzle, challenging us to rethink how extreme physics works in the universe's most violent neighborhoods. Up next, we'll dive into one of the leading theories that could crack this mystery: the elusive intermediate mass black holes, the potential missing link in the black hole family tree. Now, let's turn our attention to one of the most compelling explanations for these cosmic anomalies: the possibility that ULXs are powered by intermediate mass black holes. These elusive objects could be the missing link between the small stellar mass black holes and the supermassive giants at galactic centers. Imagine a black hole that's neither too small nor too large, somewhere between 100 and 100,000 times the mass of the Sun. That's the sweet spot for intermediate mass black holes, or IMB. If ULXs host these middleweights, their extreme brightness suddenly makes sense. A black hole of this size could devour matter at a furious rate without breaking the Eddington limit, simply because its gravity is strong enough to hold onto its meal despite the intense radiation. Evidence for this idea comes from a handful of ULXs whose behavior matches what we'd expect from IMB. Take the famous source in galaxy M82, for example. Its X-ray emissions flicker in a way that suggests a black hole of several hundred solar masses, far heavier than any stellar remnant but lighter than a true supermassive beast. Similar clues have been found in other ULXs, where the energy patterns hint at a middle ground black hole pulling the strings, but not everyone is convinced. Some astronomers argue that the same brightness could be achieved by stellar mass black holes or neutron stars under extreme conditions, like Super-Eddington accretion or beamed emissions. Others point out that IMB themselves are still theoretical. We've yet to find definitive proof they exist outside of ULXs. It's a classic chicken and egg problem. Are ULXs bright because they host IMB, or are we assuming IMB exist because we need them to explain ULXs? Recent studies have added fuel to both sides of the debate. On one hand, advanced simulations show that IMB could form in dense star clusters, where multiple black holes merge over time. On the other, observations of pulsing ULXs, clearly neutron stars, prove that not all ultraluminous sources need IMB to shine. The truth might lie somewhere in between, with some ULXs harboring middleweight black holes and others relying on different tricks to break the brightness barrier. What's clear is that if IMB are real and powering even a fraction of ULXs, they'd solve more than just this puzzle. They'd fill a glaring gap in our understanding of how black holes grow, bridging the divide between stellar deaths and galactic behemoths. Until we have more data, though, the mystery remains wide open. Next up, we'll explore another twist in the ULX saga: the discovery of pulsating sources that point to an entirely different culprit, neutron stars with unimaginable magnetic fields. Now, here's where the plot thickens. Just when we thought ULXs might all be about intermediate mass black holes, astronomers stumbled upon something unexpected: pulsating ULXs. These cosmic powerhouses don't just glow brightly, they pulse with a rhythmic beat like a lighthouse in the depths of space, and that changes everything. Pulsations are the telltale signature of neutron stars, the ultra-dense remnants of exploded stars. Unlike black holes, neutron stars have solid surfaces and insane magnetic fields, and when they spin, they can beam radiation in our direction like a cosmic strobe light. The discovery of pulsating ULXs shattered the assumption that only black holes could power such extreme brightness. Suddenly, we had proof that neutron stars, some of the smallest and densest objects in the universe, could also produce ultraluminous X-rays. Take the famous ULX in galaxy M82, known as M82X2. It pulses every 1.37 seconds, a dead giveaway that it's a neutron star, not a black hole. But here's the puzzle: how can something so small outshine entire star clusters? The answer lies in its magnetic field. Some of these neutron stars might be magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth. These fields could funnel incoming matter onto the star's surface in focused columns, creating hotspots that glow brighter than theory ever predicted. This discovery forced scientists to rethink the rules. If neutron stars can mimic the brightness of black holes, then maybe ULXs aren't a single class of objects but a mix of different cosmic engines. Some could be intermediate mass black holes, others might be stellar mass black holes pushing the Eddington limit, and now we know some are neutron stars defying expectations. It's a reminder that the universe loves to surprise us, but the story doesn't end there. These pulsating ULXs also raise new questions. How do neutron stars sustain such extreme accretion rates without blowing themselves apart? Could their magnetic fields be distorting space-time itself, bending light to make them appear brighter than they really are? Every answer leads to another mystery, and that's what makes ULXs so fascinating. Up next, we'll dive into one of the wildest ideas yet, Super-Eddington Accretion, where black holes and neutron stars gorge on matter at rates so extreme they defy physics as we know it. Now, let's venture into one of the most mind-bending ideas in astrophysics, Super-Eddington Accretion. Picture a black hole or neutron star with an insatiable appetite, devouring matter so fast it defies the cosmic speed limit. Normally, there's a cap on how bright an object can get before radiation pressure pushes material away, a boundary called the Eddington limit. But ULXs laugh in the face of this limit, shining hundreds or even thousands of times brighter than they should. So how do they pull it off? The secret might lie in chaos. Instead of matter falling in smoothly, imagine a stormy, lopsided feast. Gas and dust swirl around the compact object in clumps and streams, creating pockets where material slips through the radiation barrier. Think of it like trying to water a garden with a fire hose. Most of the water sprays away, but some still soaks the soil. In Super-Eddington Accretion, some matter manages to slam onto the surface or into the black hole's disk, releasing staggering amounts of energy in the process. But here's the twist. This frenzy isn't just about brute force. Magnetic fields could be playing bouncer, corralling incoming material into narrow columns that punch through the radiation pressure. Simulations show these magnetic funnels might focus X-rays into beams, making the object appear brighter from our vantage point, like a flashlight pointed straight at your eyes. And if the beam wobbles or precesses over time, it could explain why some ULXs flicker unpredictably. The stakes: if Super-Eddington Accretion is real, it rewrites the rules. Black holes and neutron stars could grow faster than we thought, potentially solving mysteries like how supermassive black holes got so big so quickly. It also blurs the line between ULXs and other cosmic oddballs, like tidal disruption events, where stars are ripped apart by black holes in a similar feeding frenzy. Yet, for all its brilliance, this idea isn't without critics. Some argue that what we're seeing isn't true Super-Eddington flow, but clever tricks of perspective, like a cosmic sleight of hand. Others suggest that exotic physics, like photon bubbles or warped spacetime near rapidly spinning objects, could mimic the effect. One thing's certain: Super-Eddington Accretion turns ULXs into cosmic laboratories, testing the limits of gravity, magnetism, and thermodynamics. And just when we think we've got a handle on it, the universe throws another curveball. Up next, we'll explore another twist in the ULX saga: the beamed emission hypothesis, where these objects might be cosmic fakers, shining bright not because they're powerful, but because they're pointing straight at us. Now, let's tackle another fascinating possibility. What if ULXs aren't actually as powerful as they seem? Enter the beamed emission hypothesis, a cosmic illusion that could explain their extreme brightness. Imagine a lighthouse in space. From a distance, its beam appears blindingly bright when it sweeps directly toward you, but much dimmer when pointed away. ULXs might be doing something similar, focusing their X-rays into narrow jets that happen to aim right at Earth. This idea isn't just speculation. Some of the brightest ULXs show telltale signs of beaming, like rapid flickering or unusual X-ray spectra. If their energy is funneled into tight beams, even a modestly powerful object could appear ultraluminous from our perspective. It's like holding a flashlight to your eyes versus shining it across a room. The intensity changes dramatically based on the angle. The physics behind this is wild. Magnetic fields near the compact object could twist and channel, escaping radiation into collimated jets, similar to how pulsars beam radio waves. But here's the catch: for this to work, the beams would need to stay remarkably stable over time, or we'd see ULXs dimming as they wobble. Some models suggest the accretion disk itself might act like a guide, keeping the beams locked onto Earth by sheer chance. Critics, though, point out a problem. If beaming is the answer, we'd expect to see many more faint ULXs, ones whose beams point elsewhere but they're oddly rare. This missing population puzzle makes some scientists skeptical. Others argue that beaming might only enhance the brightness of already extreme objects, not fully explain it. The debate gets even juicier when we consider that some ULXs pulse regularly, like neutron stars. If those pulses are visible, the beams can't be too narrow or we'd miss them entirely. It's a cosmic balancing act. Too much beaming and the pulses vanish, too little and the brightness doesn't add up. Whether ULXs are truly monstrous powerhouses or just cosmic tricksters depends on who you ask. But one thing's clear, their light holds clues to some of the most extreme physics in the universe. Up next, we'll explore where these enigmatic objects love to hang out, the bustling stellar nurseries of star-forming galaxies. Now, shifting our gaze to where these cosmic powerhouses tend to gather, let's dive into the bustling neighborhoods of star-forming galaxies. Ultraluminous X-ray sources have a favorite hangout spot: young, vibrant galaxies where stars are born at a furious pace. These regions are like cosmic nurseries, packed with massive stars and dense clusters, creating the perfect breeding ground for ULXs. Why do they thrive here? Think of it as a high-stakes game of stellar survival. In these crowded environments, massive stars, those weighing many times more than our Sun, often end their lives in dramatic fashion. Some collapse into black holes or neutron stars, while others explode as supernova. When these compact remnants find themselves paired with a companion star in a binary system, the stage is set for a ULX. The dense stellar environment increases the chances of such pairings, and the abundance of gas from nearby star formation provides a steady fuel supply. But there's more to the story. These star-forming regions are also chaotic, with intense radiation and powerful stellar winds shaping the surrounding space. This turbulence can funnel material toward the compact object at rates that defy normal limits, potentially triggering the Super-Eddington accretion we've discussed earlier. It's like a cosmic buffet where the food keeps piling up faster than it can be eaten. Interestingly, ULXs aren't just passive residents in these galaxies. Their extreme energy output can actually influence their surroundings, heating nearby gas and even regulating star formation in some cases. Imagine a ULX as a cosmic blowtorch, carving out bubbles in the interstellar medium and altering the chemistry of its neighborhood. This feedback loop makes them key players in understanding how galaxies evolve over time. So, while ULXs might seem like lone wolves shining brightly in the darkness, they're deeply connected to the most dynamic places in the universe. Next, we'll zoom in on one of these fascinating binary systems to see how a compact object and its stellar companion dance together in an extreme cosmic duet. Now, let's pull back the curtain on one of the most dramatic partnerships in the cosmos: ultraluminous X-ray binaries. Picture this: a dense, hungry, compact object, like a black hole or neutron star, locked in a gravitational tango with a massive companion star. This isn't just any cosmic duo, it's a high-energy relationship where one partner feeds relentlessly on the other, creating the extreme brightness we see as a ULX. Take NGC 1313X2, one of the most famous examples. Here, a compact object, likely a black hole, orbits a massive star, siphoning off its outer layers. As this stolen gas spirals inward, it heats up to millions of degrees, unleashing torrents of X-rays. But what makes this system special isn't just its appetite, it's the sheer scale. NGC 1313X2 shines hundreds of times brighter than typical X-ray binaries, pushing the limits of what we thought possible. These systems aren't just cosmic oddities, they're laboratories for extreme physics. The companion star isn't a passive victim either. Its intense stellar winds and radiation shape how material flows onto the compact object, sometimes creating erratic bursts of energy. In some cases, the feeding process becomes so chaotic that the system flickers like a candle in the wind, giving astronomers clues about the dynamics at play. What's even more fascinating is how these binaries challenge our understanding of stellar evolution. In a typical X-ray binary, the compact object might nibble at its companion over millions of years. But in ULX binaries, the feast is so voracious that it could drastically alter the star's lifespan or even trigger unusual supernova. It's a reminder that in the universe, even the most violent relationships can teach us something profound. Up next, we'll explore how some of these ultraluminous sources might not be black holes at all, but something even more exotic, with magnetic fields so strong they warp the very fabric of space around them. But here's where things get even more intriguing. Not all ultraluminous X-ray sources play by the same rules. Some might be cosmic imposters, hiding their true nature behind unimaginable magnetic power. Enter magnetars, the universe's ultimate magnetic monsters. These aren't your average neutron stars. Imagine a stellar remnant so dense that a teaspoon of its material would weigh 1 billion tons, but with a magnetic field 1,000 trillion times stronger than Earth. That's a magnetar, a force of nature so extreme it bends the very laws of physics. Now here's the twist: some ULXs might actually be magnetars in disguise. Normally, neutron stars, even the dense ones, shouldn't be able to produce the insane X-ray brightness we see in ULXs. But magnetars, their magnetic fields are so powerful they can twist spacetime itself, creating conditions where matter heats up to unbelievable temperatures as it crashes onto the surface. This process can unleash X-ray flares so intense that, from a distance, they look just like the glow of a black hole-powered ULX. Take the case of NGC 5907 ULX-1. At first glance, it seemed like a classic ultraluminous source, but closer observations revealed pulses, a telltale sign of a spinning neutron star. The kicker: its X-ray output matched ULX levels, suggesting a magnetar was behind the show. This discovery sent shockwaves through astrophysics because it proved that neutron stars, under the right conditions, could masquerade as something far more massive. What makes magnetars such compelling candidates is their ability to break the so-called Eddington limit, the point where radiation pressure should blow away incoming material, stopping further growth in brightness. But magnetars don't care about limits. Their magnetic fields can funnel matter onto their surfaces in narrow columns, bypassing the usual restrictions and allowing them to shine far beyond what should be possible. This revelation adds a thrilling layer of complexity to the ULX puzzle. If some of these bright cosmic beacons are actually magnetars, it means our census of black holes and neutron stars in the universe might need a serious revision. It also raises a tantalizing question: how many other ULXs out there are hiding similar magnetic secrets? As we peel back these layers, the universe reminds us that sometimes the most extreme objects wear the cleverest disguises. And speaking of cosmic surprises, our next stop takes us even deeper into the unknown, where some ULXs might be connected to the most violent explosions in the cosmos. Now, let's take a step back and trace the fascinating journey of how we've come to understand these cosmic powerhouses. The story of ultraluminous X-ray sources isn't just about their mind-bending physics, it's also about the brilliant tools and breakthroughs that brought them into focus. It all began in the early 1970s with a little satellite named Uhuru, the first dedicated X-ray observatory in space. Before Uhuru, X-ray astronomy was like trying to study fireworks through a thick fog. But this pioneering mission changed everything, scanning the skies and cataloging hundreds of X-ray sources. While Uhuru didn't spot ULXs directly, it laid the groundwork by proving that the universe was far more energetic and violent than we'd imagined. Fast forward to the 1990s and the plot thickens. The Rosat satellite, with its sharper X-ray vision, started picking up objects that defied expectation, sources so bright they couldn't be explained by ordinary black holes or neutron stars. These were the first hints of what we'd later call ultraluminous X-ray sources, though at the time, astronomers were scratching their heads, wondering if their instruments were playing tricks on them. Then came the game-changer, NASA Chandra X-ray Observatory, launched in 1999. Chandra's razor-sharp resolution was like swapping a blurry telescope for high-definition glasses. Suddenly, we could pinpoint ULXs in distant galaxies, measure their exact brightness, and even study their flickering patterns, one of Chandra's biggest revelations. Many ULXs weren't just random blobs of light, they were often paired with massive companion stars, suggesting they were part of binary systems. But the real twist arrived with New Star, the Nuclear Spectroscopic Telescope Array, in 2012. Where Chandra excelled at seeing fine details, New Star specialized in high-energy X-rays, the kind that reveal the fingerprints of extreme physics. With New Star, scientists could peer into the hearts of ULXs and spot telltale signs of Super-Eddington accretion or the spin of hidden neutron stars. Each of these missions built on the last, turning ULXs from cosmic oddities into laboratories for testing the limits of physics. And the journey isn't over. With next-generation telescopes like Athena and Lynx on the horizon, we're poised to uncover even more secrets. But that's a story for another day. For now, let's turn our attention to another piece of the puzzle, the mysterious link between ULXs and some of the universe's most cataclysmic explosions. Here's the next section of your script, seamlessly continuing from the previous content while introducing the new focus on intermediate mass black holes. Now, let's tackle one of the biggest cosmic riddles tied to these ultraluminous X-ray sources. Could they be hiding the universe's missing middleweight champions? For decades, astronomers have been on the hunt for intermediate mass black holes, the elusive gap between stellar mass black holes, which are a few times heavier than our Sun, and the supermassive giants lurking in galactic centers. ULXs might just hold the key to this mystery. Think of it like this: we've found plenty of black holes the size of stars and monsters weighing millions or billions of solar masses, but the middle ground, it's been eerily empty. That's where ULXs come in. Some of these extreme objects pack the brightness you'd expect from black holes, thousands of times heavier than the Sun, perfect candidates for that missing category. But here's the twist: not all ULXs behave like textbook intermediate mass black holes. Some flicker too rapidly, a signature more typical of smaller, spinning neutron stars. Others show X-ray patterns that suggest they're not just feeding greedily but might be funneling their light into narrow beams, making them appear brighter than they really are. This has split scientists into camps. One side sees ULXs as the long-sought proof of intermediate mass black holes, while the other argues they're just stellar remnants with extreme tricks up their sleeves. The debate gets even juicier when you consider how these objects form. If ULXs do host intermediate mass black holes, did they grow from smaller black holes merging in dense star clusters? Or are they ancient relics from the early universe when conditions favored the birth of mid-size monsters? Every new observation, like the discovery of a ULX in a globular cluster where intermediate mass black holes are suspected to lurk, adds fuel to the fire. One thing's clear: whether ULXs solve the mystery or deepen it, they're forcing us to rethink how black holes grow and how the universe balances its cosmic scales. And with next-gen telescopes set to weigh in, we might finally get answers. But before we jump to conclusions, there's another piece of this puzzle we need to explore: the bizarre environments where ULXs thrive, and what they tell us about the universe's most violent neighborhoods. Now, let's step into one of the universe's most extreme testing grounds. Ultraluminous X-ray sources aren't just cosmic oddities, they're nature's ultimate physics labs, pushing matter to limits we can't even dream of recreating on Earth. Imagine an environment where gravity is so intense it bends light like taffy, where densities crush atoms into exotic states, and radiation blasts out with enough energy to vaporize planets. That's the daily reality inside a ULX. What makes these objects so valuable to scientists? They're like natural particle accelerators, but on a scale far beyond anything we've built. Take the accretion disks around ULXs, swirling maelstroms of superheated gas moving at nearly the speed of light. Here, matter doesn't just behave strangely, it defies textbook physics. Magnetic fields become so powerful they twist space itself, while temperatures soar to billions of degrees, creating conditions similar to the first microseconds after the Big Bang. And then there's the radiation. ULXs don't just emit X-rays, they flood their surroundings with enough high-energy photons to strip electrons from atoms light years away. This extreme environment lets astronomers study how matter and energy interact under pressures that would instantly obliterate any human-made experiment. It's like having a front-row seat to the universe's most violent particle collisions, but without the need for a giant underground tunnel. But the real magic happens at the quantum level. Near a ULX's compact object, whether it's a black hole or neutron star, scientists suspect phenomena like photon bubbles might form, where light gets trapped in swirling eddies of plasma. Some theories even suggest spacetime itself could warp into bizarre shapes, creating lenses that amplify the object's brightness. These effects aren't just sci-fi. They're real-world tests of Einstein's general relativity and quantum mechanics in their most extreme forms. What's thrilling is how ULXs challenge our engineering limits. While we struggle to sustain fusion for milliseconds in tokamaks, these cosmic powerhouses maintain reactions millions of times more energetic for centuries. They're teaching us about energy efficiency at scales we've never considered, lessons that might one day revolutionize how we harness power here on Earth. As we peer deeper into these natural laboratories, each discovery peels back another layer of the universe's rulebook. And with every observation, we're not just solving cosmic puzzles, we're rewriting the laws of physics as we know them. Next up, we'll zoom in on some of our galactic neighbors hosting these extraordinary objects and what their proximity reveals about the ULX phenomenon. Now, let's take a cosmic road trip to some of our galactic neighbors, where ultraluminous X-ray sources aren't just distant specks but close enough to reveal their secrets. The Cartwheel Galaxy, for instance, is a stunning ring-shaped galaxy about 500 million light-years away, and it's home to several ULXs that have become prime targets for study. Because these objects are relatively nearby, at least by cosmic standards, astronomers can observe them with unprecedented detail, peeling back layers of mystery that would otherwise remain hidden. What makes these nearby ULXs so special? Their proximity allows telescopes to capture finer features, like the exact structure of their accretion disks or the way their X-rays interact with surrounding gas. In the Cartwheel Galaxy, for example, researchers noticed something peculiar. The ULXs there are often found in regions bursting with young, massive stars. This clue suggests a direct link between ULXs and the explosive lives of these stellar giants, hinting that they might be the remnants of supernova or hypernova. Then there's the Whirlpool Galaxy, just 31 million light-years away, where a ULX named NGC 5194X1 has been flashing like a cosmic beacon. Because it's so close, scientists have tracked its brightness fluctuations over years, revealing patterns that challenge traditional black hole models. Sometimes it dims unexpectedly, as if something is temporarily blocking its X-ray output, a behavior that's hard to explain unless the object is feeding in fits and starts, or perhaps has a companion star with an irregular orbit. Even our galactic backyard, the Andromeda Galaxy, holds surprises. A ULX called CSOM 31J4043+41159, despite its mouthful of a name, has shown pulses of X-rays that suggest it might actually be a neutron star, not a black hole. This discovery was only possible because Andromeda is close enough for sensitive detectors to pick up these subtle signals. It's a reminder that ULXs might not all fit into one neat category. Some could be neutron stars pushing the limits of physics, while others are black holes breaking the rules. Studying these nearby ULXs is like getting a front-row seat to the universe's most extreme physics experiments. Their proximity lets us test theories in real time, watching how they evolve and interact with their environments. And with every observation, we're not just solving puzzles about ULXs, we're uncovering clues about how galaxies grow, how stars live and die, and how the universe itself operates under the most extreme conditions. Next, we'll see how cutting-edge telescopes like Neutron Star are taking our understanding of these cosmic powerhouses to the next level. Now, let's shift our gaze to the cutting-edge tools that are cracking the code of these cosmic enigmas. NASA's Neutron Star telescope, with its unparalleled ability to detect high-energy X-rays, has been a game-changer in understanding ultraluminous X-ray sources. Unlike earlier telescopes that could only see lower energy emissions, Neutron Star peers into the most energetic corners of the universe, revealing details about ULXs that were once invisible. One of its biggest breakthroughs came when it analyzed the spectral signatures of several ULXs, essentially their X-ray fingerprints. These signatures showed features that didn't match predictions from traditional black hole models. For instance, some ULXs emitted X-rays with unexpected dips and peaks, suggesting their accretion disks might be warped or their magnetic fields far stronger than anyone imagined. This data ruled out the idea that all ULXs are simply smaller black holes feeding at extreme rates, forcing scientists to reconsider their assumptions. Neutron Star also spotted something even more surprising. Some ULXs flicker in ways that can't be explained by pure accretion alone. These rapid brightness changes, happening over mere minutes, hint at complex interactions between the compact object and its surroundings, like a neutron star's magnetic field shredding incoming material or jets of plasma colliding with gas clouds. Without Neutron Star high-energy vision, these clues would have remained hidden, leaving theories about ULXs stuck in the dark. Perhaps most importantly, Neutron Star observations help debunk the notion that ULXs are all the same. By comparing their spectra, researchers realized these objects fall into distinct groups, each with unique traits. Some behave like supercharged pulsars, others like black holes defying the Eddington limit, and a few defy classification entirely. This diversity means no single theory can explain every ULX, pushing astrophysics toward more nuanced explanations. Thanks to Neutron Star, we're not just guessing about ULXs anymore, we're testing ideas with hard data. Every high-energy X-ray it captures peels back another layer of mystery, bringing us closer to understanding how these cosmic powerhouses truly work. And as we'll see next, the story gets even more intriguing when we explore the bizarre flares that make some ULXs shine like cosmic Christmas trees. Now, let's venture into one of the most fascinating and speculative corners of ULX research: the possible connection between these cosmic powerhouses and hypernova, the universe's most violent stellar explosions. Imagine a star so massive that when it dies, it doesn't just collapse into a black hole or neutron star. It detonates with a force 100 times greater than a typical supernova. These hypernovae are rare, but their aftermath might hold the key to understanding some ultraluminous X-ray sources. Here's the intriguing idea: what if certain ULXs aren't just feeding black holes or neutron stars, but are instead the remnants of hypernova? When a hypernova explodes, it can leave behind a dense, rapidly spinning core, either a black hole or a magnetar, surrounded by a chaotic debris field. If this core starts devouring the leftover material at an insane rate, it could produce the extreme X-ray brightness we see in ULXs. Some scientists argue that this scenario would explain why certain ULXs are found in star-forming regions where massive stars, and thus hypernova, are more likely to occur. There's even tantalizing evidence to back this up. A handful of ULXs have been spotted near the remnants of past supernova or hypernova, almost like cosmic crime scenes where the explosion's aftermath is still visible. In these cases, the ULX's X-ray emissions seem to match what you'd expect from a hypernova's leftover core, gorging on the surrounding wreckage. It's as if the star's death didn't just create a compact object, it set the stage for a second act of cosmic violence. But here's the twist: not all hypernova remnants would become ULXs. The conditions have to be just right. The core must spin fast enough, the debris field dense enough, and the magnetic field strong enough to channel material onto the compact object at Super-Eddington rates. That's why this connection remains speculative, though incredibly exciting. If proven, it would mean some ULXs aren't just exotic objects, they're the resurrected corpses of the universe's most colossal stars. Of course, this isn't the only explanation for ULXs, but it's a compelling piece of the puzzle. And as we'll see next, the mysteries only deepen when we consider how quantum physics might be warping the environments around these cosmic monsters. Now, let's take a step into the bizarre and mind-bending world of quantum physics, where the rules we know start to break down, especially near ultraluminous X-ray sources. These cosmic monsters don't just push the limits of brightness, they might also twist the very fabric of reality in ways we're only beginning to understand. Picture this: near a ULX, the gravitational pull is so intense that space-time itself warps, bending light and distorting the paths of particles. Under these extreme conditions, quantum effects, usually too subtle to notice, become impossible to ignore. One wild idea is the formation of photon bubbles. Imagine X-ray photons trapped in the swirling chaos around a ULX, clumping together into unstable pockets of energy. These bubbles could amplify the object's brightness, making it appear even more luminous than it already is. It's like a cosmic funhouse mirror, but for radiation. Then there's the mind-blowing concept of warped spacetime altering how energy escapes. Near a ULX's compact object, gravity is so strong that it might focus X-rays into narrow beams, like a flashlight in a dark room. This could explain why some ULXs seem impossibly bright. What we're seeing isn't just raw power, but energy channeled and magnified by the extreme environment around it. But here's where it gets even stranger. Quantum mechanics suggests that in these ultra-dense regions, particles might behave in ways that defy classical physics. Virtual particles, usually popping in and out of existence too quickly to matter, could get caught in the gravitational whirlpool, creating bursts of radiation or even influencing how material falls onto the compact object. Some theories even propose that ULXs could be testing grounds for exotic physics, like quantum gravity effects that blur the line between Einstein's relativity and the quantum world. Of course, these ideas are still on the cutting edge of astrophysics. We don't have direct proof yet, but missions like NASA's upcoming Lynx telescope could change that. For now, ULXs remain not just cosmic anomalies, but potential windows into the universe's most extreme physics. And as we'll see next, their brilliance might even help us measure distances across the cosmos if we can crack their code. Now, let's shift gears and explore an intriguing possibility. Could ultraluminous X-ray sources serve as cosmic measuring sticks? Astronomers have long relied on objects like Cepheid variable stars, whose predictable brightness changes help gauge distances across the universe. But ULXs, with their staggering luminosity, might offer a new way to map the cosmos. If we can decode how they work, think of it like this. If a ULX's brightness follows a consistent pattern, similar to how a lighthouse emits steady flashes, we could use it to calculate distances. The brighter the ULX appears from Earth, the closer it likely is. But here's the catch: this only works if their extreme emissions aren't distorted by beaming, Super-Eddington accretion, or other wild physics we've discussed. Some researchers argue that certain pulsating ULXs with regular X-ray pulses might hold the key. If their spin rates and brightness are linked in a predictable way, they could become standard candles for the high-energy universe. Imagine measuring the distance to a galaxy millions of light-years away just by observing its ultraluminous X-ray sources. It's a tantalizing idea, but one still tangled in uncertainty. Of course, challenges remain. Unlike Cepheid variables, ULXs are messy and unpredictable. Their brightness can flare or dip without warning, and their environments are chaotic. Plus, without a solid grasp of what's truly powering them, black holes, neutron stars, or something else, it's hard to trust them as cosmic yardsticks. Yet, if future telescopes like Athena can untangle these mysteries, ULXs might revolutionize how we chart the universe. And speaking of revolution, there's another fringe idea worth mentioning. Could dark matter play a role in these cosmic powerhouses? That's a question that takes us even deeper into the unknown. Now, let's venture into one of the most speculative corners of ULX research. Could dark matter somehow fuel these cosmic monsters? It's a wild idea, but some scientists have dared to ask whether the invisible stuff making up most of the universe's mass might play a role in these extreme X-ray sources. Here's the thinking. If dark matter particles collide and annihilate near a black hole or neutron star, they could release enormous energy, potentially explaining ULX's ridiculous brightness. Picture it like throwing gasoline on a fire, except the gasoline is an exotic particle we've never directly detected. The math kinda works in theory, but there's a glaring problem. We still don't know what dark matter actually is. Critics point out that ULXs are found in star-forming regions, where ordinary matter is already dense enough to power them without invoking shadowy physics. Plus, if dark matter were the secret source, we'd expect ULXs to behave very differently, like appearing in empty galactic voids where dark matter dominates. Instead, they're cozying up to young stars and gas clouds. That said, science thrives on bold ideas, and this one isn't completely dismissed. Some models suggest certain types of dark matter could accumulate around compact objects, creating a slow-burning energy reservoir. It's a long shot, but if future telescopes catch a ULX flaring in a place where normal matter is scarce, the dark matter hypothesis might get a second look. For now, though, it remains a fascinating what if a reminder that the universe loves to keep its deepest secrets just out of reach. And speaking of secrets, let's turn to the next big question. How will tomorrow's telescopes crack the ULX code? Now, let's peer into the future, because the next generation of telescopes might finally unravel the secrets of ultraluminous X-ray sources. Imagine instruments so advanced they can dissect the light from these cosmic powerhouses with precision we've only dreamed of. Leading the charge are missions like Athena and Lynx, set to launch in the coming years. Athena, the advanced telescope for high-energy astrophysics, is Europe's answer to the ULX puzzle. With a mirror larger than any X-ray telescope before it, Athena will capture faint X-ray signals with stunning clarity. Think of it as putting on glasses after years of blurry vision. Suddenly, details hidden in the noise become crystal clear. This could help us spot subtle changes in ULX emissions, revealing whether they're powered by Super-Eddington accretion, intermediate mass black holes, or something even stranger. Then there's Lynx, NASA proposed X-ray observatory. If approved, Lynx will boast resolution 100 times sharper than Chandra, the current gold standard. It's like upgrading from a flip phone to a microscope. Every flicker, every pulse from a ULX could tell us something new. Lynx might even catch the telltale signs of magnetars masquerading as ULXs, or spot the faint glow of dark matter interactions if they exist. But it's not just about sharper images. These telescopes will analyze X-ray spectra, the energy fingerprints of ULXs, with unmatched accuracy. Tiny dips or spikes in those spectra could betray the presence of warped spacetime, extreme magnetic fields, or even exotic quantum effects near the event horizon. And here's the kicker: future missions won't work alone. Combining Athena and Lynx's X-ray data with gravitational wave detectors or neutrino observatories could paint a multidimensional picture of ULXs. It's like solving a puzzle by feeling the pieces, hearing them click, and seeing them fit all at once. The bottom line: we're on the brink of a revolution in understanding these cosmic anomalies. With every technological leap, ULXs move from being tantalizing mysteries to potential keys for unlocking the universe's most extreme physics. And that's a future worth waiting for. Now, let's take a detour from hard science and step into the realm of imagination, because ultraluminous X-ray sources have also sparked some wild and fascinating ideas in science fiction. These cosmic monsters, with their mind-bending energy output, have become a goldmine for storytellers looking to push the boundaries of the possible. Picture this, an advanced alien civilization that doesn't just orbit a star but builds a megastructure around a ULX, tapping into its unimaginable power. Some sci-fi writers have imagined Dyson sphere-like constructs around these objects, harvesting energy that could fuel entire interstellar empires. Others have used ULXs as natural cosmic lighthouses, guiding lost ships through the void or marking the locations of hidden wormholes. Then there's the darker side of the fiction. What if a ULX wasn't just a natural phenomenon but a weapon? Some stories have explored the idea of a rogue black hole or neutron star being artificially steered into a ULX state, turning it into a doomsday device capable of sterilizing whole star systems. It's the kind of apocalyptic tech that makes for gripping space operas, but perhaps the most intriguing use of ULXs in fiction is as a narrative shortcut for faster-than-light travel. If a ULX's extreme physics bends spacetime enough, could it create a stable gateway to another galaxy? Sci-fi loves playing with this idea, using ULXs as cosmic shortcuts or as the mysterious power sources behind alien super engines. Of course, real ULXs don't quite work like their fictional counterparts, but that's the beauty of sci-fi. It takes the mysteries of the universe and runs with them, turning scientific curiosity into epic tales of exploration, danger, and discovery. And who knows, maybe one day the truth about ULXs will be just as thrilling as the stories they've inspired. Up next, we'll look at how you can actually help scientists uncover more of these cosmic enigmas through citizen science projects. Now, here's something truly exciting. You don't need a PhD or a giant telescope to help uncover the secrets of ultraluminous X-ray sources. Thanks to citizen science projects, anyone with an internet connection can dive into real astrophysics research and potentially spot these cosmic powerhouses hiding in telescope data. Platforms like Zooniverse bring the universe to your fingertips. Imagine scrolling through images from space telescopes like Chandra or New Star, marking unusual bright spots that could be ULXs. Scientists simply can't sift through all that data alone, so they rely on sharp-eyed volunteers to flag the most intriguing candidates. It's like a cosmic treasure hunt, and you could be the one to spot something no one's noticed before. What's incredible is how much impact these projects have. Amateur discoveries have led to follow-up studies, published papers, and even new classifications of ULXs. You're not just clicking buttons, you're contributing to real science, helping professionals piece together the puzzle of these extreme objects. And the best part, no prior knowledge is needed. Tutorials guide you through what to look for, making it accessible whether you're a seasoned stargazer or just curious about the cosmos. This is science at its most democratic. By joining in, you're part of a global community pushing the boundaries of human knowledge. Who knows, the next big breakthrough in understanding ULXs might start with someone like you spotting an anomaly from their living room. And speaking of breakthroughs, let's shift gears to another jaw-dropping aspect of ULX, is their ability to unleash the fastest winds in the universe, racing outward at speeds that defy imagination. Now, let's talk about something that will truly blow your mind literally. Ultraluminous X-ray sources don't just shine brighter than anything else in the cosmos. They also unleash winds so fast they could cross the entire United States in less than a second. These aren't your everyday breezes. We're talking supersonic outflows screaming through space at over 10% of the speed of light. That's more than 60,000 miles per second, a velocity so extreme it defies everything we know about how matter behaves under normal conditions. So how does this happen? Picture a compact object like a black hole or neutron star gorging itself on material from a nearby star. As gas spirals inward at insane speeds, friction and magnetic fields heat it up to millions of degrees, creating intense radiation pressure. But here's the twist: instead of just glowing, some of that energy gets funneled into jets and winds, launching material outward like a cosmic fire hose. These winds aren't gentle, they're so powerful they can strip away entire atmospheres from nearby planets and reshape the surrounding galaxy, and the impact. It's colossal. These winds carry enough energy to heat up interstellar gas, shutting down star formation in their vicinity. Imagine a ULX acting like a cosmic blowtorch, carving out bubbles in its host galaxy and altering its chemistry for millions of years. Some researchers even think these outflows could explain why certain galaxies have dead zones where no new stars are born. But the real kicker: these winds might also solve a long-standing mystery: how ULXs manage to shine so brightly without tearing themselves apart. By ejecting material at such insane speeds, they could be balancing the scales, shedding excess energy to avoid self-destruction. It's like a pressure valve for the universe's most extreme objects. Now, as we wrap our heads around these supersonic phenomena, let's zoom out even further. What if ULXs aren't just cosmic oddities but key players in the grand story of galaxy evolution? That's a puzzle we'll tackle next. Now, let's step back and consider the bigger picture. These ultraluminous X-ray sources aren't just dazzling cosmic spectacles. They might actually be shaping the very galaxies they call home. Think of them as celestial architects wielding unimaginable energy to sculpt the environments around them. But how exactly do they leave their mark? For starters, those supersonic winds we just talked about don't just vanish into space. They slam into surrounding gas clouds, heating them up so intensely that star formation grinds to a halt. It's like throwing a bucket of water on a campfire. The raw material for new stars gets scattered or vaporized before it can collapse into stellar nurseries. In some galaxies, this could explain vast, eerily quiet regions where young stars are conspicuously absent. But here's where it gets even more fascinating. While ULXs might suppress star formation in their immediate vicinity, their energy could also trigger it elsewhere. Those blistering winds and radiation can compress distant gas clouds, squeezing them just enough to kickstart new generations of stars. It's a cosmic domino effect, one extreme event setting off another millions of years later. Then there's the chemical legacy. ULXs are factories for heavy elements, forged in the violent accretion process and spewed out by their winds. Over time, these elements mix with interstellar gas, enriching future stars and planets with the building blocks for everything from rocky worlds to life itself. Without ULXs, the universe might lack the diversity of elements we take for granted today. Of course, not all scientists agree on their long-term impact. Some argue that ULXs are too rare or short-lived to significantly alter entire galaxies. Others counter that even a handful of these powerhouses could leave fingerprints detectable billions of years later. The debate is far from settled, but one thing's clear: ULXs are more than just bright anomalies. They're potential game changers in the story of how galaxies grow, evolve, and seed the cosmos with new stars. And speaking of cosmic seeds, our next stop takes us even deeper into the unknown, where the bizarre behavior of ULXs might hold clues to something even more elusive. Now, let's turn our gaze to the future, where the secrets of ultraluminous X-ray sources might finally be unlocked by a revolutionary approach. Imagine detectives piecing together a cosmic crime scene, but instead of fingerprints, they're using X-rays, gravitational waves, and even ghostly neutrinos to solve the mystery. This is multi-messenger astronomy, and it could be the key to cracking the ULX puzzle in the coming decade. Right now, we're mostly limited to studying ULXs through their X-ray emissions, like trying to understand a fireworks display by only seeing the sparks. But what if we could also feel the shock waves and smell the gunpowder? Gravitational wave detectors like LIGO and Virgo could sense the ripples in space-time caused by massive collisions or disruptions near ULXs, events invisible to traditional telescopes. Meanwhile, neutrino observatories might catch particles flung out from the extreme environments around these objects, offering a direct peek into their violent hearts. Combine these clues and suddenly the picture gets sharper. For example, if a ULX flares up in X-rays at the same moment a gravitational wave detector picks up a tremor from its direction, we'd have smoking gun evidence linking it to a black hole merger or a neutron star's explosive demise. Neutrinos could confirm whether matter is being shredded at near light speed, ruling out some theories while boosting others. It's like assembling a jigsaw puzzle where each piece comes from a different corner of physics. The real game changer, upcoming projects like the Einstein Telescope and the Cosmic Explorer, next-gen gravitational wave observatories with sensitivity so sharp they could pinpoint ULX activity in distant galaxies. Pair them with advanced X-ray telescopes like Athena and neutrino detectors like IceCube Gen 2, and the 2030s might deliver breakthroughs we can barely imagine today. Of course, challenges remain. ULXs are rare and their signals are faint, like trying to hear a whisper in a hurricane. But with multi-messenger astronomy, we're no longer relying on a single sense to decode the universe. We're building a toolkit that listens, watches, and even feels the cosmos in ways that could rewrite our understanding of these dazzling enigmas. And as the data pours in, one thing's certain: the story of ULXs is about to get a lot more interesting. Up next, we'll explore a ULX phenomenon so strange, it's been nicknamed the Christmas tree of the cosmos, but its flickering lights are anything but festive. Now, let's shift our attention to one of the most puzzling quirks in the ULX universe, a phenomenon so peculiar, astronomers have playfully dubbed it the Christmas tree anomaly. Picture a cosmic string of holiday lights flickering on and off in deep space, except these flashes aren't festive decorations. They're bursts of energy from an ultraluminous X-ray source pulsing with eerie regularity. What makes this behavior so baffling? Most ULXs shine with a steady, relentless glow, but a handful like the famous M82X2 flare up at predictable intervals, sometimes every few hours or days. It's as if someone's flipping a switch, turning the brightness dial up and down in a cosmic light show. Scientists first thought these patterns might stem from a wobbling disk of superheated material, like a tilted record on a turntable, but the precision of the timing hints at something far stranger. One leading theory points to the ULX's magnetic field acting like a cosmic gatekeeper. Imagine a neutron star with a magnetic field so intense it funnels incoming material into narrow columns. As the star spins, these columns sweep across our line of sight like a lighthouse beam, creating periodic flashes. But here's the twist: some Christmas tree ULXs pulse too slowly for this to be the sole explanation, suggesting another player might be at work. A warp in the accretion disk itself, wobbling like a spinning top and periodically blocking our view. Then there's the wild card. Could these flares be caused by clumps of matter crashing into the compact object at uneven intervals? Picture logs tumbling into a bonfire, some igniting instantly while others smolder before bursting into flame. If the companion star feeding the ULX sheds material in irregular chunks, these collisions could trigger the rhythmic brightening we observe. Yet the Christmas tree mystery deepens when we consider that not all pulsing ULXs behave the same way. Some flicker like candle flames while others flash with military precision. This diversity has astronomers scratching their heads. Are we looking at multiple phenomena masquerading under one name, or is there a universal mechanism we're just beginning to grasp? What's clear is that these cosmic light displays are more than just celestial oddities. They're clues hinting at the extreme physics governing ULXs, from warped spacetime to magnetic chaos. And as telescopes grow sharper, each flicker brings us closer to untangling the truth behind the universe's most enigmatic holiday lights. Up next, we'll pit ULXs against their fiery cousins, microquasars, in a showdown of cosmic extremes. Which reigns supreme in the X-ray universe? Stay tuned. Now, let's turn the spotlight to a cosmic heavyweight match: ULXs versus microquasars. Both are dazzling X-ray powerhouses, but what sets them apart? Think of microquasars as the smaller, more familiar cousins of quasars, packing a punch within our own galaxy. These systems consist of a black hole or neutron star feeding off a companion star, launching jets of particles at near light speeds. They're bright, they're dynamic, and they've been studied for decades. But ULXs, they take everything we know about microquasars and crank it up to 11. Microquasars, like the famous SS433, operate within the Eddington limit, the point where radiation pressure balances gravity. Their jets and X-ray flares are impressive, but they play by the rules. ULXs, on the other hand, laugh in the face of those rules. They blast out X-rays at intensities that defy physics textbooks, sometimes millions of times brighter than microquasars. How? That's the million-dollar question. One key difference lies in their feeding habits. Microquasars consume material at a steady, predictable rate, like a well-mannered diner. ULXs, though, seem to gorge themselves, swallowing gas and dust at unsustainable speeds. This Super-Eddington feasting could explain their outrageous brightness, as matter piles up faster than it can radiate energy away. Some scientists even suggest ULXs might be microquasars on cosmic steroids. Their jets so tightly focused they appear brighter from our vantage point. Then there's the scale. Microquasars are homegrown, found within the Milky Way and nearby galaxies. ULXs, by contrast, prefer the bustling stellar nurseries of distant star-forming galaxies. Their environments are denser, richer in young, massive stars, perfect fuel for their extreme appetites. And while microquasars occasionally flare, ULXs maintain their blinding glow for years, even decades, making them the marathon runners of the X-ray universe. But here's the twist: some ULXs might actually be microquasars, just viewed from a special angle. If a microquasar's jet points straight at us, its light could be amplified, mimicking a ULX's brilliance. This beaming effect blurs the line between the two, leaving astronomers debating where one ends and the other begins. So who wins this cosmic showdown? In raw power, ULXs take the crown, but microquasars hold their own as crucial laboratories for understanding jet physics and accretion dynamics. Together, they remind us that the universe has more than one way to create extreme X-ray phenomena, and that the brightest objects often hide the most tantalizing secrets. Up next, we'll spin into another mystery: how black hole rotation might supercharge ULXs, turning them into the universe's ultimate power plants. Don't touch that dial. Now, let's take a closer look at another piece of the ULX puzzle: black hole spin. Imagine a figure skater pulling their arms in to spin faster. Black holes do something similar, and this cosmic pirouette might be the secret behind ULX's jaw-dropping brightness. When a black hole rotates rapidly, it doesn't just sit there. It drags space-time around it, creating a whirlpool of energy. This spin affects how matter falls in, twisting the accretion disk into a tighter, hotter frenzy. Simulations show that a fast-spinning black hole can squeeze more energy out of every bit of gas it swallows, like revving an engine to its limits. The result? X-rays that outshine even the most optimistic predictions. But here's where it gets wild. A spinning black hole doesn't just boost luminosity, it changes the rules of the game. The Eddington limit, that old ceiling on brightness, starts to crack under these extreme conditions. Matter piles up faster than it can radiate energy away, creating a traffic jam of particles glowing white-hot. Some models suggest spin might even focus X-rays into narrow beams, amplifying their apparent brightness from our viewpoint. Yet spin alone isn't the whole story. ULXs likely need a perfect storm: a rapidly rotating black hole, a generous donor star, and a dense feeding environment. Get all three, and you've got a recipe for cosmic fireworks. Next up, we'll tackle a question that's equal parts science and sci-fi. Could these monstrous energy factories ever pose a threat to Earth? The answer might surprise you. Now let's shift gears and tackle a question that sounds like it's straight out of a sci-fi thriller. Could these ultraluminous X-ray sources ever pose a danger to Earth? The short answer is no, but the long answer is way more interesting. First, let's put things in perspective. The nearest known ULX is millions of light years away, far beyond our Milky Way. Even if one were closer, the real threat isn't the brightness, it's the physics at play up close. Picture this. If you could somehow stand near a ULX, the intense X-ray radiation would strip atoms apart in seconds, and the gravitational forces would spaghettify anything that dared to wander too close. But here's the good news: space is vast, and ULXs are cosmic loners, minding their own business in distant galaxies. What about the idea of a rogue ULX drifting into our neighborhood? The universe doesn't work that way. These objects are tied to their host galaxies, and the chances of one getting kicked out and hurtling toward us are astronomically low, literally. Even if it happened, we'd have plenty of warning, thanks to the way light and gravity travel at finite speeds. So, while ULXs are undeniably terrifying up close, they're no more a threat to Earth than a fireworks display on the other side of the planet. But that doesn't make them any less fascinating. Their extreme physics pushes the boundaries of what we thought was possible, reminding us just how wild the universe can be. Next, we'll dive into an even bigger cosmic mystery. Could advanced civilizations harness the power of ULXs? The possibilities are as mind-bending as the objects themselves. Now, let's stretch our imaginations even further and ask, could an advanced civilization out there actually harness the insane power of an ultraluminous X-ray source? It's a wild thought, but when you break it down, the idea isn't as far-fetched as it sounds. Think about it. If a society mastered technology far beyond ours, they might see ULXs not as cosmic oddities, but as potential power plants. The energy output of just one of these objects could dwarf the entire consumption of a civilization for millennia. Picture a Dyson sphere, but built around a ULX instead of a star, a megastructure designed to siphon off that unimaginable X-ray energy. Theoretically, it's possible, but here's the catch: we've never spotted anything like it. This brings us face to face with the Fermi paradox, the puzzling silence of the cosmos despite the high probability of alien civilizations. If ULXs are such obvious powerhouses, why haven't we detected any signs of them being used? One explanation is simple: maybe no civilization has reached that level yet. Or perhaps the physics around ULXs is too extreme, even for advanced beings. The radiation, the gravity, the sheer violence of the environment, it might be too hostile to tame, no matter how advanced the tech. Another possibility: they're already using them, but in ways we can't detect. Maybe their engineering is so advanced it leaves no trace we'd recognize. Or worse, what if harnessing a ULX's energy is a civilization's final act, a desperate move that leads to self-destruction? It's a chilling thought, but it would explain why we haven't stumbled across any ULX-powered super-civilizations. So while the idea of aliens tapping into these cosmic monsters is thrilling, the silence of the universe keeps it firmly in the realm of speculation for now. But as we peer deeper into the cosmos with better telescopes, who knows what we might uncover? The line between science and science fiction has never been thinner. Next up, we'll zoom in on one of the strangest behaviors of ULX, is those bizarre, flickering flares that light up like cosmic Christmas trees. What's causing them? The answer might rewrite the rules of astrophysics. Now, as we wrap up our journey through the mysteries of ultraluminous X-ray sources, one thing is crystal clear: these cosmic powerhouses are rewriting the rules of astrophysics right before our eyes. ULXs aren't just bright, they're cosmic rebels defying every textbook limit we've ever set. From smashing the Eddington limit to flaring like celestial Christmas trees, they force us to question what we thought we knew about black holes, neutron stars, and the very fabric of space itself. But here's the thrilling part: we're only scratching the surface. With next-generation telescopes like Athena and Lynx on the horizon, the next decade could crack open these enigmas in ways we can't yet imagine. Picture this: we might finally confirm the existence of intermediate mass black holes, or uncover entirely new physics lurking in those supersonic outflows. Every flicker, every flare from a ULX is a clue waiting to be decoded. So stay curious. The universe is far stranger, far more violent, and far more beautiful than we've dared to dream. And who knows, the next big breakthrough might come from an unexpected flicker in the data, or even from you, as citizen scientists sifting through telescope feeds. The cosmos is full of extremes, and ULXs are just the beginning. If you're as fascinated by these cosmic anomalies as we are, don't forget to hit that subscribe button and ring the notification bell. There's so much more universe to explore, and we're just getting started. Until next time, keep looking up, because the next cosmic mystery could be just a beam of X-rays away.